This video is for Module 5, Part 1, and includes a discussion of the mean, median, and percentiles. Okay, let's go ahead and get started. So the mean and median are measures of location. In particular, they're measures of center of a distribution. These types of measurements should be computed only on numerical data or numerical measurements. So a numerical variable is a set of measurements that is on a naturally numeric scale. Okay, now that might seem straightforward. However, that's not always the case. Let us consider this data that I have presented here on the screen. The baby name is certainly not numeric. In fact, it's just a string of characters put together. Gender, the 1 is being used to identify the females, and a 2 is being used to identify the males. So even though these are numbers here, it's not on a naturally numeric scale because they're just identifying the gender. In other words, it would not make sense to compute an average for that gender column. The weight is listed in grams here. That is on a naturally numeric scale. Weight in pounds and ounces is also on a naturally numeric scale. We have units here, but those units can just be removed, and what would be remaining is a set of numbers or a collection of numbers. Mother's age is on a naturally numeric scale. And then things like month and day are kind of not really on a naturally numeric scale. Okay, so 7 here is just indicating July. 11 would indicate November, so that's kind of like gender. Day, we don't really have an alternative representation for 6, other than that's the 6th day. But again, these are just identifying positions throughout the month. So again, I'm not sure if it makes sense to compute an average day here. So even though they're numbers, determining whether or not the average or median is useful needs to be considered before computing those quantities. So the appropriate summaries for categorical variables include things like counts, percentages, bar graphs, etc. The summaries that are appropriate for data on a naturally numeric scale include things like the mean, median, standard deviation, etc. Now there are a wide variety of characteristics in numerical data that can be summarized. This wide variety of summaries will be discussed throughout the various parts in this module. Some of those characteristics that we are interested in is location or position. That's what's being considered here. Things like the spread in the data, the shape in the data, and then identifying outliers or unusual observations will also be considered later on in this module. So let's consider example 5.1.1. Here what we are looking at is snowfall amounts across the state of Colorado. We have information from 180 different weather stations provided here. We have the snowfall amounts broken out for each month. So you can see in the summertime, June, July, and August, there's not very much snow at all that falls in the state of Colorado. The variable that I want to summarize here is the total. So the total is simply the sum throughout the year for each of those different weather stations. And again, there's 180, quite a list of weather stations included here. Here's a picture of the locations of those weather stations in Colorado, and you can see that they are dispersed throughout the entire state. And then there's also information about the counties provided in that data. So there's the various counties for the state of Colorado. Okay, so here is a dot plot of the snowfall amounts across those 180 different weather stations. So each dot on this map represents a particular weather station in that data set. You can see that the smallest amount, so there's some areas in Colorado that don't receive very much snow at all. And then there's other areas of Colorado that receive quite a bit of snow. And these measurements are in units. You can see quite a few of the weather locations have snowfall amounts between 20 inches and maybe 90 inches or 80 inches here. So a lot of the data is clumped down here on that lower end. I'll let you answer the questions that are provided here. So go ahead and hit pause and try to answer those questions. Okay, let's talk about measures of center. So the most common measures of center for a set of numerical measurements are mean, median, and mode. Now the mode is commonly included in this list. However, the mode is only a measure of center when the distribution is peaked at the center. So in practice, statisticians do not use the mode as a measure of center. And for that reason, it will not be considered any further here in our discussions. So the mean or the average is simply to sum up all of the data values and divide by the number that we have, so the number of data values. How do we compute the median? The median is just the middle value of a set of numerical measurements. We need to first put those in order to calculate the median. So the 5 measurements for weight in grams, we simply add those up, and we have 5 measurements, so we would divide that by 5. The median is we need to place those numbers from smallest to largest, so arrange those in order, and then we simply cross off from each end until we end up in the middle. So the median for those 5 numbers would be 2554. Okay, so we are going to compute measures of center using a spreadsheet. So in order to compute the mean or the average, we're going to use the equal average function, as is stated here. And the median, we're going to use the equal median function. So here, the various snowfall amounts, the totals here, are in cells 02 through cell 0181, I believe it is. So if we slide over here to the right, you can see that's how I would compute the average and the median total snowfall amounts for this particular data set. Now there is an easier way to specify what data that you want to have summarized, and that's using something called named ranges. So what I can do is specify the data which exists in cells 02 through 0181. So I can specify that set or collection of cells. I can give that set or collection of cells a name. So down below here, I'm showing you if I give that set, if I give that set a name, say total snowfall, then what I can do is just type equal average total snowfall in my formula. I don't have to specify the individual cells. So all of this has been shown using a video here. I created a short video to show you how to use named ranges and then also compute the average and the median for a set of data. So I'll let you watch that short video. Okay, so when an average is computed for a set of numbers, the information contained in these measurements is reduced or condensed. So here I have that dot plot that was created above of the 180 different weather stations. And if I compute an average, the average was 64.7 inches. Okay, that average just simply represents the balance point in that distribution. So by computing an average, what I have done is taken all 180 measurements and condensed them down to a single value. Now there are certainly advantages to doing that. For example, it's a lot easier to make comparisons when I have a single value than when I have many values. So consider the snowfall amounts from 3 different counties: Grand County, Larimer County, and Otero County. So how different are the snowfall amounts in these counties? Okay, that's kind of hard to quantify. We can see that Otero seems to be quite low. Okay, Larimer seems to be kind of spread out more than Grand. But if I ask you to just make comparisons between these 3, that's kind of hard to do. However, if I compute an average, so if I condense these measurements down to a single value for each county, making comparisons is much easier. So I can see that Grand County, for example, gets about 40 more inches of snow compared to Larimer County. Or that Otero is at about 20 here for average snowfall amount. So one major advantage of computing an average is it allows me to more easily make comparisons across here different counties. The median is guaranteed to be the middle value in a data set. So here I have 180 measurements, and for this large data set, I would just cross off the largest, cross off the smallest, and then I would just keep going until I get down to the middle, which here is going to be in between the 90 and 91st measurement, which for this data, I guess, is 64 or 46.45. Okay, so for the Colorado snowfall example, the mean and median are, so for this example, the mean and median are 64.7 inches for the mean and 46.45 inches for the median. Now here, there's quite a difference between these two measures of center. And the reason that is because of the heavy tail on the right side of this distribution. So this right tail here is much longer, or fatter we might say, than the left side. And what that does is it drags the mean up. Okay, so a right tail, a long right tail like this, is going to drag that mean up a little bit. And actually drags it up quite a bit here. As I said a moment ago, the mean is about 20 units higher than the median. So another thing is that an outlier can have an adverse effect on the mean. Okay, so when I look at the formula for a mean, it uses every single data value that gets put into that formula. So if just one data value starts to become very, very large, what that's going to do is drag that mean up. That doesn't happen with the median, because with the median, what happens is that's the first observation that gets crossed off. So again, as soon as I calculate the median, I'm going to eliminate the largest value and then the smallest value and just continue through. So that large value is not going to, that could grow, that could be 10 times larger, and that's not going to have any impact on the median because it's the first observation that gets eliminated. So for that reason, we say that the outliers tend to affect or will affect an average much more than the median. So when they compute or when they discuss income levels in the United States, we almost always use median household income instead of average household income. And the reason they're reporting the median is because of this fact. One person's income could really throw off an average. Okay, so let's talk about a more general measure of location. So here I'm going to talk about percentiles. And for the percentile discussion, I'm going to use income data that I got from the Census Bureau. And the data that we are considering here is just the income values for the state of Minnesota. These values are given by county. So there are a total of 87 counties in Minnesota. Okay, so Winona County is down here somewhere towards the bottom. And we can see that for Winona County, the average income per household is about $54,000. Or the median, I guess it's the median household income here, is the $54,000. So I got that information on all 87 counties across the state of Minnesota. So what do we mean by percentiles? So a percentile is just, the definition here is the pth percentile for a set of measurements is defined to be the point in the data where p% of the measurements fall below. Okay, so here again is the dot plot for the household incomes for the state of Minnesota. There are 87 dots. The median household income for one county, this poorest county in Minnesota, looks like it's at about $42,500. And then it reaches all the way up to $95,000 for other counties. Again, this kind of has a right tail that's longer than the left side. So what do we mean by the 0th percentile? Well, the 0th percentile, the interpretation there is that's the value for which 0% of the points fall below. So the 0th percentile is simply the minimum value in the data set. On the other hand, the 100th percentile would be the maximum value of the data set. Again, 100% of the values are going to fall below that point. Now we've already talked about the median, but the median an example of the 50th percentile. So the 50th percentile means that I'm halfway through the data points. And that, by definition, is what the median is. So we can do things like what percent of the, so if I have a question, what percent of the income values fall below 70%, what you're really asking for is the percentile. So I'm asking what percent fall below the 70%, or excuse me, fall below 70,000 here. What I need to do is just count the number of data points that are in that gray region. So I guess there are 76 points out of the total 87 in this region. So 76 divided by 87 is the 87th percentile. So 70,000 would be considered the 87th percentile in this set of measurements. So here in the table on the right, okay, I just have specified income levels and their associated percentiles. So 55,000 is the 51st percentile, so that's pretty close to what the median value is here. Again, the median is the 50th percentile. An alternative approach to identifying various locations would be to set up the percentiles at particular set points. So here I'm getting the 0, 10, 20, 25th, 30, so a variety of percentiles here. And then I'm just getting these values, the household income values. So here the 50th percentile is going to be the median. So the exact median in this data set is 54,645. We have these other things, the median of the lower half of the data, that would be the 25th percentile, is about 51,000. And then the third quartile, which is the median of the upper half of the data, is just about 60,000 here. So there's a couple of different ways that we can compute percentiles. Now if I look at this table here, or this table here, okay, the most common way of looking at those tables is through something called a cumulative density function plot. And that's what is being displayed here. So the measurements, household income levels, are put on the x-axis of this plot. So if we look at the x-axis on this plot, you can see those are income levels. The y-axis includes the various percentiles. So if I wanted the 50th percentile, or the median in the set of data, all I would need to do is just select percentile 50th and slide over until I hit the line and then drop down. And you can see that that's about 55,000. If I wanted the 90th percentile, or maybe I want to identify incomes for the top 10%, then I would slide over for 90th percentile until I hit the line and then go down. And again, that looks like it's somewhere between 70 and 75,000. So for the counties in Minnesota, the top 10% have incomes above about $70,000. We can work the graphic backwards as well. So a moment ago, we were talking about what percent was at 70,000 or less. So I can set the 70,000, go up till I hit the line, and then move across. And looks like I'm somewhere between the 85th and the 90th percentile. So from up above, I think we calculated that to be the 87th percentile. So this graphic right here, the cumulative density function, is probably the most useful display for understanding percentiles. It's a very common display. So I'll let you answer the questions about this CDF plot. You can determine things like minimum and maximum here. Question 6. The minimum value is just where it hits 0 here. So at about 42,500 is where it hits 0. So that would be the smallest value in the data set. The maximum would be up here on the when it hits 100%. So up here close to $95,000. So there's one particular county in Minnesota that has a median household income of roughly $90,000. Let's talk a little bit about this region that I've identified here. This is for question number 8. This region here, you can see that the CDF plot is very, very steep. And what that means, the steepness, what that indicates is that I have a lot of people in this range. Okay, so I have I guess these are counties here for the 87 counties. So I have a lot of counties between 45,000 and 65,000. You can see that 45,000 is basically close to the 0th percentile. 65,000 is about the 85th percentile. So 85% of the people, or 85% of the counties, I guess here, have incomes between $45,000 and $65,000. So when the CDF plot is very steep like this, that means you are accumulating a lot of measurements because the percentiles are increasing quickly. When we get above 65,000, you can see that the steepness decreases quite a bit. And again, what that means is that I don't have very many counties, or excuse me, the upper end of the distribution for incomes is spread out quite a bit. It goes from 65,000 up to 95,000. So those counties that are on the upper end of the income scale, again, what is that, about the top 15%, are spread out in their incomes. Okay, so how do I get percentiles using a spreadsheet? So again, we just identify what values we want to compute the percentiles for. I have created a short video to show you how to do that. We just need to specify a range of percentiles that you're interested in. And then I'm going to just use the equal percentile function. So again, there's a short video here that shows you how to do that. And then I've also described the steps that you can go through in Google Sheets to accomplish that task. You can create the CDF plot here in Google Sheets as well. I've created this for the Minnesota County income data. One disadvantage of using Google Sheets here is it's pretty hard to actually connect the various dots. So don't worry about connecting the dots on your CDF plot. That'll suffice for this course. Okay, one major advantage of using CDF plots is in making comparisons. So here I have income levels for Minnesota on the top, Virginia in the middle, and Wisconsin on the bottom here. So I'll hit pause here and let you answer the two questions that we have here before going on. Okay, so what I've done here is I've taken the average of each of those three states. So the average of Minnesota seems to be about 55,000, maybe a little bit bigger than 55,000. Virginia seems to be real close, a little bit bigger than 55,000. And then Wisconsin is also just slightly below the 55,000. So when I compute the average, it looks like the income levels in these three states is pretty consistent, or at least the average income level across those states is pretty consistent. However, when you compute an average and reduce the measurements down this much, we're going to lose information. In particular, you're going to lose information about the amount of variation that exists in Virginia. So if we go back up and look at our original data, you can see that the counties in Virginia are spread out much more than in Minnesota and Wisconsin. Minnesota seems to be slightly more spread out than Wisconsin, and that's mostly due to these counties on the right-hand side. These counties on the right-hand side tend to be the counties around the Twin Cities, so they tend to be a little bit more wealthy than some of the other counties in Minnesota. But you can see in Virginia we have several fairly wealthy counties, and those are going to be counties that are close to Washington, D.C. On the other end of Virginia, we have several poor counties as well, and these will be in the southern part and western part of Virginia. So when I compute the averages, I lose that information about income disparity when making comparisons across these three distributions. However, when I look at a CDF plot, it includes the entire spectrum of income levels. So here is a CDF plot for Minnesota, Wisconsin, and then also Virginia. So I have a set of questions here that I would like you to answer regarding this CDF plot. I'll just make some quick notes. We can see that in the middle of the distribution, the three states are pretty similar. Okay, so around the median here and even around the 60th percentile in this distribution, those three states have very similar income levels. However, on the low end, we can see that Virginia is set back quite a bit. So let's take the 20th percentile. For example, you can see that Virginia's 20th percentile is at about 40,000, whereas Minnesota's 20th percentile is up over 50,000. That's about a $10,000 difference, which might not seem like a lot, but we're talking about incomes around 40 and 50,000. So 10,000 is quite substantial when you're talking about income levels at 40 or 50,000. Now on the upper end of the distribution, so again this here is Virginia, you can see that Virginia has shifted ahead. Okay, so the Virginia CDF plot here, or the cumulative density function for Virginia, is somewhat flatter than for Minnesota and Wisconsin. And what that means is they have much more income disparity. Their measurements are spread out much more because it's not as steep as Minnesota and Wisconsin. Okay, so I'll let you try to answer these questions here, and you submit those, and then you can look at the solutions that I have provided. Okay, that does it for Module 5, Part 1. Thank you.